First, let me tell remote learners something. So for remote learners, I moved all the code word submissions to exit ticket because it was getting too crowded on assignments. Yeah, the daily code words. I do it to see if they're actually watching the videos. To make sure, because I have to have some way of taking attendance. And so if I do only a video, there's no way I know that they watched the video. Oh, am I the only teacher doing videos? Well, I'm saying, am I the only teacher doing videos? Because I'm imagining all the other teachers are passing out notes and doing something else. Alright. So, we learned in class that force is equal to mass times acceleration. The 8th. So, force is equal to mass times acceleration. If your mass is in kilograms, your acceleration is in meters per second squared, then the force can be written in newtons. No. I was going to work out some F equals ma examples. So, suppose you had a cannon and a $10-kilogram cannonball. Suppose you launch the cannonball and it exits the cannon at 100 meters per second. And it spends only 0.1 seconds in the cannon. How much force was exerted on the cannonball? So suppose you had a cannon and a 10-kilogram cannonball. Suppose you launch the cannonball and it exits the cannon at 100 meters per second. It spends only a tenth of a second in the cannon. How much force was exerted on the cannonball? So we know that our force equation F equals ma. We know our mass is going to be on the cannonball. So our mass is 10 kilograms. Or acceleration. What's the equation for acceleration? Over time. So our final velocity, this would be the 100 meters per second. So that's your VF. Is 100 meters per second. Before you fire the cannon ball, how fast is it moving? 0. So before you launch it, it's not moving inside the cannon. Before you actually fire it. So our initial velocity is 0. And how long was it in the cannon? 0.1 seconds. So its acceleration is 1,000 meters per second squared. So we have our acceleration, our mass. We can plug these in. So mass and acceleration. And so we get 10 kilograms times 1,000 meters per second squared. And we see the force on the cannonball would be 10,000 newtons. So that's a lot of forces that are on the cannonball. Make sense? Alright. 10,000 newtons. So if your mass is in kilograms, your acceleration is in meters per second squared. It's technically 10,000 kilogram meters per second squared, but we can replace the units with the letter N for Newton. Yes. So if your mass is in kilograms, your acceleration is meters per second squared, you can replace these two units with just the letter N. Suppose you push on a shopping cart you push on a shopping cart with a force of 1,000 newtons, causing it to accelerate at 5 meters per second squared. How much mass does the shopping cart have? Suppose you push on a shopping cart with a force of 1,000 newtons, causing it to accelerate at 5 meters per second squared. How much mass does the shopping cart have? So remember, our equation is F equals ma. We can make a triangle. F would go on top, M and A would go on bottom, and we're solving for mass. So mass is equal to force over A. Or force is 1,000 newtons or acceleration is 5 meters per second squared. So 1,000 divided by 5 is 200 kilograms. Again, if your force is in newtons, your acceleration is in meters per second squared, your mass is going to be in kilograms. Make sense? Suppose you push the shopping cart with mass 200 kilograms with only 200 newtons, or no, with only 400 newtons of force. What acceleration would it have? So again, F equals ma. We're solving for A. So A is equal to force divided by mass. Or force is now 400. Our mass is 200 kilograms. And so it would be 2 meters per second squared. Assuming it started at rest, what would its speed be? What would its speed be at after 5 seconds? So suppose you push the shopping cart with has 200 kilograms of mass. So assuming you push the shopping cart that had 200 kilograms of mass, 400 newtons of force. Assuming it started at rest, what would its speed be after 5 seconds? So we know that the acceleration is 2 meters per second squared. And we're asking what would its speed change by? It started at rest. How much would its speed change? So if you think back to acceleration is equal to change in velocity over time. Vf minus Vi over time. We're trying to figure out how much is changed its velocity. So its change in velocity be equal to acceleration times time. We already calculated that the acceleration is 2 meters per second squared, and our time is 5 seconds. So its final speed would be 10 meters per second. Makes sense? All I'm doing is adding F equals ma to what we've already looked at. Applying it to our acceleration equation. Not today. I'll do it tomorrow. Yes. For remote learners, here's the code word. This is the code word for remote learners. You don't need to know. Y'all need to put y'all's mask on if you're not wearing it. Daniel, mask. Yeah, you are within 2 meters of each other. You'd have to be over 2 rows. There'd have to be an empty row between you and another person. Yes. What's up? Not really. I don't. Not a sports teacher. Well, that's why you wear the mask. If the entire basketball team or whatever sport you're in gets sick, then if you're wearing a mask, you won't spread it to anyone else. Y'all wear a mask. Alright, let's do another example. Guys, cool it. So, during takeoff, a 500 kilogram plane, very light plane, undergoes an acceleration. 2.2 pounds. Yep. 1100. Or what would that be? So 500 kilograms is equal to about 1100 pounds. So, undergoes acceleration. Yes. Once Amanda gets back. During takeoff, a 500 kilogram plane undergoes an acceleration of 10 meters per second squared. How much force does the propellers push on the plane? You can go. How much force does the propeller exert on the plane? So solve that one. The math should be easy enough to do in your head. Exert. Like, don't ever exert yourself. Since our acceleration is in meters per second and our mass is in kilogram, we can write our force in newtons. Oh, Amanda, put on your mask. So did y'all get an answer? What'd y'all get? So F equals ma. Our mass is 500 kilograms. Our acceleration is 10 meters per second squared. So that would be 500 kilograms times 10 meters per second squared. Since they're just being multiplied, you multiply the units together. So that'd be a kg times a meter per second squared. But since it's in kilograms and meters per second, we can replace this with newtons. If it was in pounds and miles per hour, we would just it would be pound miles per hour per second. Makes sense. Suppose you're on a faraway planet. You measure the mass of a rock to be 20 kilograms and weigh it and find it weighs 800 newtons. What is the acceleration due to gravity? So try working that one out. Oh, that's what we're trying to figure out. Put your mask on and keep it on. What'd y'all get? So what'd you get? Alright. So we see the force exerted on it is gravity, 800 newtons. The mass is 20 kilograms. So F equals mass times acceleration. Solving for acceleration. Acceleration is equal to F over m. F is 800 newtons. Our mass is 20 kilograms. And we get 40 meters per second squared. So this is over 4 times as strong as the gravity on Earth. So if you were to be on this planet, you'd weigh 4 times as much. you probably wouldn't be able to stand too well, if at all. Do a few more examples. So you push with a force of 200 newtons on a box, causing it to go from 10 meters per second to 20 meters per second in 5 seconds. Where is the mass of the box? So you push with a force of 200 newtons on a box, causing it to go from 10 meters per second to 20 meters per second in 5 seconds. What is the mass of the box? Anyone got an answer? 2 kilograms? So we know we're finding mass, so we'll use the F equals ma equation. Solving for mass. So mass is equal to F divided by A. We know that the force is 200 newtons. But what's the acceleration? The acceleration is final minus initial over time. So we would take its final. This is VF, this is our initial, VI, and this is our time. So it'd be 20 meters per second minus 10 meters per second over a time of 5 seconds. So that'd be 10 meters per second divided by 5 seconds, or 2 meters per second squared is their acceleration. So we plug that in for A, and we get that the box weighed 100 kilograms, or about 220 pounds. So the general step in solving these is begin by writing down F equals ma, figuring out the correct form the equation should be in. So we're solving for mass. Mass is equal to force divided by acceleration. You ask yourself, what was the force? Where's the acceleration? The force was given, 200 newtons, but the acceleration was not. If it doesn't tell you the acceleration, you're going to have to solve for it using the acceleration equation. Acceleration is equal to final velocity minus initial velocity over time. Alright, let's do a more complicated one. A 20 kilogram box has a 50 Newton force on it. Causing it to go from, let's see, 0 meters per second. Let me make sure these numbers make sense before I do it. To go from 0 meters per second to 25 meters per second. How long was the force being applied to the box? So a 20 kilogram box has a 50 Newton force on it, causing it to go from 0 meters per second to 25 meters per second. How long was the force being applied to the box? So we're asking about time. So we're solving for t. Let's begin by, so we know that acceleration is equal to Vf minus Vi over t. So we're solving for this t. If we put this in triangle form, circle t, we see time is equal to final velocity minus initial velocity over acceleration. But we don't know what acceleration is yet. We know that our final velocity, 25, and our initial velocity is 0. So we don't know what acceleration is. To solve for acceleration, we'd use F equals ma. Solving for acceleration, acceleration is equal to F divided by m, or force is 50 newtons, our mass is 20 kilograms, so that'd be 50 newtons divided by 20 kilograms, are 2.5 meters per second squared. This is our acceleration, so we can plug it into here. So that'd be 25 meters per second over 2.5 meters per second squared, or 10 seconds. So we were applying a force of 50 newtons on a 20 kilogram box for 10 seconds, and how it caused it to go from 0 to 25 meters per second. So the only thing that's really different is we're applying now F equals ma. It's still the same techniques. We begin by identifying variables and equations and solving for variables. We just now have two different equations to work with at the same time. So if we're solving for t, we need to use the equation that has t in it. But we don't know what the a is in the equation. So we have to use the other equation to solve for a. Any questions? Alright, I believe that's where I'm going to stop for today.